Good morning or afternoons. So our project is called M17 Mosaic Montage Workflow by using HTCondor or NFS server. So this project was focused on using a distributed system to execute a large-scale astronomical image processing workflow efficiently. So large-scale astronomical workflow require high computing power and involve multiple dependent tasks. So when these workflows are executed manually on a single machines, the process is slow in its efficiency and also prone to failure. So without proper job scheduling and shared storage, the task may be failure or remain idle. Therefore, a distributed system is needed to automate the executions, manage the task dependency, and also improve overall efficiency. Let's talk about the objective of this project. So first, to deploy a functional distributed system using HTCondor for scheduling, and also the NFS server for shared storage. Second, to execute the Montage m17 mosaic workflow successfully and generate the final astronomical image. So finally, to gain the practical experience by identifying the challenge and learning how to resolve them in a distributed system.
My name is Montage and I'll be talking about project overview and tools and technology used. So first of all is project overview. The main idea of this project was to solve a scalability problem. We know that modern scientific experiments like processing astronomical data are too heavy for a single computer to handle efficiently. If you run this task manually on one machine, it will take days. So our high-level concept was to build a distributed, high-throughput computer cluster. So instead of relying on one powerful supercomputer, we use a cluster of smaller standard server. We connected them in a way that makes them act like a single unified system. The technology and tools we have used first of all is for our infrastructure. We use AWS EC2. We use AWS because it gives us on-demand scalability. We deploy Ubuntu servers as our nodes. This allowed us to simulate a real-world data center environment without needing physical hardware. So for our brain, we use a cluster called HTCondor, and this is our workload manager. We didn't want to manually log into every server to run scripts. So basically, HTCondor does this for us. It uses a mechanism called class add to match jobs with an available machine. Its main benefit is maximizing resources utilization. So as long as the node finishes a task, HTCondor will immediately gives it a new one, so there's no time wasted and it works efficiently. Next is for our data management. We implement a network file system, NFS. This is critical because in a distributed system, a common problem is that node A has the data, but node B needs to process it. With NFS server, we create a shared folder that looks local to every machine. This means all our nodes can read the input files and read the output files to the exact same place, eliminating the need to constant copy files back and forth. So next is our use case. We use a Montage engine because we needed a real scientific workload to test our system, not just a simple hello world script. So Montage is perfect because it requires complex dependencies. Some tasks can run in parallel while others can run waiting for the previous step. So these are basically all the technology we have used for this project.
Hello everyone, I'll be explaining about the system architecture of our mosaic montage workflow that runs on the HTCondor for distributed job executions. This architecture is designed to efficiently handle large-scale astronomical image processing by distributing the workloads across multiple machines while keeping the data access centralized. The system is made of four main components: a submission host, content master, execution host, and a shared NFS storage, all working together to manage job submissions, scheduling, executions, and data storage in a structured and efficient way. The workflows begin at the submission host, where the user submits a montage workflow in the form of a DAG file. The submission host is responsible for receiving this workflow and translate it into the HTCondor job description, such as the .sub files. These submission files, along with all required inputs data, are written directly into the shared NFS storage. By doing this, you ensure that every node in the system has access to the same sets of files, which is critical for consistency and smooth executions. Once the job is submitted, control is handed over to content master, which acts as the central scheduler for the system. The content master keeps track of available resources, including the execution host, and decides when and where its task should run. It manages the job status and continuously communicate with the execution host to monitor the progress and handle the scheduling decisions. When the task is scheduled, the execution host takes over the computation. It retrieves the necessary input data and submission files directly from the NFS server, executes the assigned montage processing task, and then writes all output data, logs, and results back to the same shared storage. Because all data access, all the data access happens through the NFS server. There's no need for manual file transfer between the machines, which improve the efficiency and reduce the risk of errors. The NFS system plays a critical role in the architecture by acting as a centralized shared file system. Both the submission host and execution host rely on it to read input files and store results, ensuring the data consistency across the entire workflow, as well as simplifying the coordination between the nodes. This system architecture clearly separates the responsibilities of job submission, schedule, executions, and storage. By combining the HTCondor's powerful distributed scheduling with NFS-based shared storage, we achieve a scalable and reliable solution that is well suited for running large montage workflows.
Hi guys, I'm Jun. So next I'm going to talk about the workflow. So the workflow will distribute the command into each task, and the task will running from task A until task M. This task will be running in linear condition. So next, this is the sample job file, which the executable will represent the command that we need to run, and the argument will be represent the input needed for this command. And you can see this is the sample we can be output in our AWS. So next is our linear DAG file. This DAG file reveals the dependency of each task. So task B only can run when task A is finished. And next is our output file. And you can see this all the output after running all the tasks. And I'll show you the demo now. So now I am in our assignment directory, and I will show you how we run our workflow in order to create the final mosaic m17 image. So now everything is ready, and we just submit it. Condor submit underscore DAG workflow.dag. Okay, we can see one job is submitted to cluster 101. And we can go to Condor queue and see what is the status. Now it's ideal, and we need to wait for a while in order for it to ready all the tasks and finish it. Okay, now finally the final image, which is m17 underscore mosaic.png, is done, and we can take it and see what is the final image. And we put tag inside. Take some time, wait to run. Okay. Now we can see the final image, the m17 final mosaic image, which is something like this, which is exactly same with the documentation given, the same. Okay, that's all for my demo. Workflow.DAGman.log. See with DAG. DAGman.log, and you can see how it runs and how long it takes. So it started at 703 and ended at 7:08. So it takes around 4 minutes to execute the whole process. That's all from me. This is the demo for workflow for linear to run the m17 mosaic in order to process the final image m17 mosaic.png. That's all from me. Thank you.
Hi, my name is Eugene Tong, and today I'll be presenting the results and observation. For the montage workflow, we have executed successfully using linear DAG. Jobs were scheduled and executed across multiple execution nodes. NFS was enabled for seamless shared file access among machines. Final m17 mosaic image was generated successfully. The challenges and solutions. Problem 1. When we first ran Montage by ourselves, we do not know how to set up the environment for running Montage. Therefore, we were unable to run some commands like make and mjpeg in Montage m101. Solution. We have learned from our lecturer about how to set up the environment in our lab test tree, and we realized that we need to have a GCC compiler to compile Montage source code in order to run some code. When we run the workflow DAG for the first time, we did not realize we haven't chmod 777 for some important file like diffdir, cordir, capcordir. Therefore, the task will be idle because the machine cannot access to those important files. Solution. Since we realized it by running Condor Q better analyze, we found out that those important files cannot be accessed by other machines and the other tasks keep being in an idle state. Therefore, we ran chmod 777 on important files to make sure when machine executes the task.sub files, the machine were able to access those important files. Problem 3. Our sub file did not have enough memory to run the request command. Therefore, the Condor job status cannot be saved and will be in a hold status and will not continue running. The solution. There are not enough memory for running the command. Therefore, we decided to add request memory to 1 GB in order to run the following command. Problem 4. Initial jobs remain idle state because of executable path point to user local bin instead of mount data Montage bin, which caused the machine to not be able to find the command listed in the path. The solution. We check back the environment settings from the lecturer and change the path for every task to ensure every worker node could locate the command in the correct pathway. For future improvements, increase the number of execution nodes to improve performance. Implement parallel DAG workflow instead of linear execution. And we need to optimize CPU and memory allocation for jobs. Add monitoring and logging visualization for better analysis. Conclusion. Distributed systems deployment with HTCondor and NFS. Successful execution of Montage m17 workflow. Linear DAG job dependency management. Efficient task scheduling and shared storage. Enhance practical knowledge in distributed system and workflow automation. Improve understanding of environment setup, file permission, and resource allocation. Thank you.